Hello, and welcome to Backer Breaks It Down. In this episode, we are going to take a look at similarity and transformations. So, similarity transformations consist of a dilation or composition of one or more dilations and one or more congruence transformations. So, what that means is that there needs to be a dilation and or a reflection, rotation, or translation. Two figures are similar if and only if there is a similarity transformation that maps one figure onto the other figure. So let's determine whether two figures are similar, shall we? Use the definition of similarity in terms of similarity transformations to determine whether triangle DEF is similar to triangle ACB. Explain your reasoning. So the first thing I notice is that triangle DEF has a base of 6 units and a height of 3 units. Triangle ACB has a base of 2 and a height of 1. So clearly there's a dilation that reduced this triangle, okay? And I'd say by a scale factor of 1/3. Now, when you are describing similarity transformations, I would keep it simple, meaning keep your dilations with like a center of dilation at 0, 0. I think that's like the easiest thing to do. Okay. And so if I do that dilation, what I end up with is this. So let me get this tool out. So I would end up, here we go. That would be the new DEF. So D would now be at -3, 2, and E would be at -1, 2, and F would be at -1, 3. So then in order to complete this similarity transformation, I would have to translate my new triangle D prime, E prime, F prime down and right. And so I'd have to go down 1, right? And then I'd have to go right 5. And that would map triangle DEF onto ACB. So they are similar to each other because I came up with a similarity transformation that maps triangle DEF right onto triangle ACB. The figures shown are similar. Assume that the figure on the left is the pre-image. So that would be this one. List the sequence of transformation that verifies the similarity of the two figures. So I think one is pretty obvious. I mean, okay, yeah, there's a dilation, but I really think it's a good idea to get the figures oriented the same way before you go like doing the dilation. It's just my own personal preference. So I would honestly start by reflecting quadrilateral RSTU over the y-axis. So it looks like this, okay? So reflect over the y-axis. And then I would perform the dilation because there is clearly a dilation. So I want to dilate this figure by a scale factor of 1/2. And like I said before, I would definitely use the origin as the center of dilation because that's going to be easier. And so when I dilate this by a scale factor of 1/2, I think that's it. It like totally maps it onto WXYZ. And then in this one, okay, now obviously because I have these rules right on the screen, we want to do a rotation, but it's like when you look at triangle LMN, yes, I do want to rotate this triangle and I want to go clockwise. I want to go 90 degrees clockwise, okay, this way. And so I did that, right? I did a 90 degrees clockwise rotation. Once again, using the center or the origin as the center of rotation. And then from there, I can see that, of course, I need to perform a dilation in order to get it to be the same size as triangle RST. And it's looking like I need to dilate it by a scale factor of 2. And I should definitely use the center of dilation at the origin, because that's just going to make it easier. And so I just need to confirm that that's all there is to it, and then I'll be done. So let's see. So that means this point here is currently at 3.2. When I dilate it, I'm going to be at 6.4. So that checks out. So these two similarity transformations prove that these two figures are similar to each other. Okay, so basically two figures are similar if and only if there is a similarity transformation that maps one figure onto the other. So that means a dilation and something else. Translation, rotation, reflection. And that's how Becker breaks it down.